So good morning, everyone. So first of all, I thank the organizers of this FDP on machine learning for signal processing for giving me an opportunity to share the topic video analytics for human behavior recognition. So today, actually, my presentation will be, so I'll be giving you an introduction about the video analytics in general. Then we can see about the application areas with video analytics. And then we can discuss about each and every, that is the processing steps in video analytics. So a general framework of video analytics. And in particular, we can discuss about two applications if time permits, one with emotion recognition, another with action recognition. So the general introduction, a typical video surveillance systems. What are the subblocks involved in the typical video surveillance system in brief? So when you see this code, a smile, you are on camera and the person watching could be a world away. So it indicates that. So if you're going out for a shopping mall or even to our colleges or to a hospital, even in a small shops or in even some of the houses, we have installed this surveillance camera. And so if you are going out, at least we will be in view of 2 to 3 cameras. Yes, but at different viewing angles and as well as in different orientation at different scales it will be. So that is what the statement indicates, and what generally this video surveillance is for is, so it is a system that monitors the behavior or activities of a people or the vehicle, whatever it may be, or other objects from a distance by means of an electronic equipment. So nowadays, although there are multiple cameras being installed everywhere, it can be used for the data collected from this video surveillance cameras. It can be used for the real-time analysis, or it may be used for a post-mortem work. That is, after the occurrence of such events, we will be taking the snapshots or taking the footages from the video cameras, and we will be analyzing what happened at that instance. Okay, so which is just a post-mortem work. But generally, a video surveillance system should be at a real-time analysis, that so it should prevent before particular event or abnormality occurs. So the scope of this video surveillance system, so it includes the detection of the events. So we have to detect what kind of abnormal events occurs, and we can prevent. So if you are detecting abnormal event, it is not a closed loop system. So we need to prevent. So before the occurrence of the event, or we can, so how we can react to such events. So for example, if so someone is getting for a help, or someone is asking for a help, so how we can, how the surveillance system, how the intelligence system can react to give some help to that intended person. Or if some problem is about to occur, so it should intervene and to stop the particular abnormal event. So this is what a typical video surveillance systems, as well as the scope of the video surveillance system. Then the challenges include here is, so nowadays, although there are many cameras installed everywhere, so who is monitoring such footages? So in some cases, there may be a dedicated person involved, maybe dedicated person is allotted for monitoring such abnormal events occurring. And in some cases, there may be, that is, for example, a cashier, he is there to get the cash. At the same time, he may also be look into the footages, and he will be monitored 2 works at a time. So it is not at all efficient. So if a particular security person allotted for analyzing the crime, to analyzing the videos present or video footages, then how long he could able to concentrate and see there. So it may be, so at worst case, the research says that he could able to concentrate for 20 minutes without losing the focus. And also, there will not be a single foot in a single frame or in a single monitor. Will not be a single frame feed, but we'll get a multiple feeds. So maybe at least 24 or 15 or maybe 12. So there in cases, what actually happens is we will be concentrating on one footage. Okay, so although we are getting feed from some 12 or 10 cameras, we will be concentrating on one footage thinking that some abnormal events is about to happen there. But actually the abnormal event will not be happening at that instance, but the people may fool us doing some event in another viewpoint. This may happen. Okay, so and another important thing is, so how this I have told you that it is really a boring thing, because the abnormality will not occur always. Okay, so it will, if you are monitoring for an 1 hour, the abnormality even will not happen for the entire 1 hour. So it is not interesting to look into the monitor and see what is actually happening. So it is a time, it is actually a boring process, and we will lose our concentration there. And so nowadays our objective is how to turn this video surveillance from a reactive tool to a proactive instrument. So nowadays it is, just as I mentioned, it is used as a that is reactive tool, that is as a post-mortem work. After the occurrence of the event, we are taking the footages of that location, and we are analyzing what actually happened at that place. But it is just a post-mortem work after the occurrence of the event. But it is good if we could able to give the alarm at the time, or so before he thinks to do it, then it is a good surveillance or a good intelligence system. But thinking of it, it is a very, very complicated process. That is, there is a small hairline between the normal event as well as the abnormal event. Okay, so the designing such a system is a very tough process. So the solution is an intelligent video. The intelligent video is a collection of technical solutions that makes it possible for systems and people to efficiently cope up with large amount of video data. So video analytics, it's meant for the passive cameras that is changing to a smart proactive sensors. So our objective is, so it's not really just giving you the feeds, but also it should be a proactive sensor. That is the objective of an intelligent video. So that some capabilities of the intelligent video includes automatically analyzes and tags surveillance video in real time and detects suspicious activities, intimates video recordings, alarms or other actions, alerts operator or the field personnel. So these are some of the capabilities of an intelligent video system. So here, so they are the, so when you see in case of your CCTV market outlook, the Indian video surveillance camera market is expected to grow with CAGR about 27.2% in the period from 2016 to 2021. And so they are some of the leading companies for who are involved in the video surveillance camera production, as well as that is and producing its accessories. Okay, so what is the challenges in intelligent video surveillance? The events are complex events. Okay, so they are not simple events or atomic events, but it consists of complex events. And as I have told you prior, it is very difficult to distinguish between the normal event as well as the abnormal event, because there is a small hairline between the normal event as well as the abnormal event. So final, and also the system should work for 24/7, night and different light conditions. So usually when you see this image processing applications, so it is subjected to illumination changes. Some of the features will change with respect to illumination changes. Then it must be susceptible to different weather conditions, and multi-scale, multi-sensor data inputs, and also another thing is privacy. So here, if you're trying to record a video, or if you're trying to capture a video at a public location, so the awareness to the people arriving there should be given. So that is what in every places it will be written as you are under surveillance. Okay, so the privacy also should be maintained. And another important thing is the installation of the camera is very, very important role in this application. See, so for example, when you are installing that is the surveillance system in an ATM, so it should be located in such a place that the abnormal event of the person should be monitored, but the pin numbers what he is typing should not be in the view of the camera. Okay, so these are the certain constraints that we have while installing that is a surveillance system in any application scenarios. So here, let me say you some few applications that can be done with this video surveillance. So one will be the video motion detection. So for example, if there are cameras installed and so it is working for 24/7 and recording in a video recorder, digital video record, DVR. So actually what will happen is after a period of 7 days, depending upon its bit rate as well as its size, its resolution, so it will try to overwrite. So and the data, when you are trying to capture such information, two constraints that need to be carefully observed. One is the transmission bandwidth, if you are trying to transmit from one location to another, and second one will be the capacity, that is the storage space. Yes, so these two things will need to be considered. And so when you see this application of video motion detection, so for example, if a camera is installed in a classroom, so our working hours is from 9 to 4, and after 4, if the classroom is closed, there is no possibility of occurring of any abnormal events. Okay, so and from the morning hours, if the first person comes inside the classroom, if some person is detected, then the recording can start. Okay, so this is one of the potential application where we can use this video motion detection. So when certain person comes, so in case of the classroom, when the first student enter the classroom, the person has to be detected and it has to say that there is some change and now you start recording. Okay, so this is the thing, so that the bandwidth as well as the storage space can be saved. And second one is tampering alarm. Okay, so nowadays the people are clever. That is, first they'll know the location of the camera and that is the field of view of the camera. Then they'll try to block the camera. So and they'll carry out with their abnormal activities. So when how this camera can be tampered? The camera can be tampered by having a spray painting, or when a high intensity light is made to focus on this camera, so it will not get the clear view of that particular location. Then camera defocusing or the camera movement. So these things can happen if you're trying to tamper the cameras. So how this tampering can be identified? As soon as if we identify, or else a simple thing is we can cover the camera with a cloth. Okay, so usually when your camera is set, it will. So I have to tell you one thing. When you're seeing the surveillance cameras, okay, I'll explain when I'm telling about the processing steps. But here, when cameras were installed, surveillance cameras were installed, it is installed at certain heights, and the field of view is fixed. Yes, since it is a fixed camera, the field of view will be fixed. So what actually maybe the background region at least, or the color, that is the nature of the color elements that is present in the particular scene can be learned initially. And if there is certain change, so if it is tampered, then the camera, the region may be blurred completely, or what can be happened is your so heavy light can be flowed, so everything will be blocked out. Okay, so or else the background can be changed. Okay, so if such things are detected, then at once the alarm can be raised. So it can be this one tampered by a particular person, or second case, this can also be happened due to the camera, some issues with your camera itself. So if there is some issues with the camera, or if some bird or so even a small insect comes in front of the lens, then the entire viewpoint will not be clear. So in such situations, itself it can give an alarm so that the technicians can come and clear out the defaults or faults that has been happened. So these are the two examples. So where there is the camera is blurred, the image is blurred due to the effect of the that is due to the tampering effect. And second, this is actually the general scenario, and the histogram is plotted here. And if it becomes completely, if it is blocked, it becomes completely black, and this histogram is there. Histogram is shown here. So by seeing the difference between the two histograms, we can identify that something has happened to the that particular location or to the camera. And another thing is auto tracking. So if you are monitoring a large region, or if you are monitoring a single person, we can fix the person and the camera will automatically zoom and follow the moving person or the vehicles. So here we have PTZ camera in the market. PTZ stands for pan, tilt and zoom cameras. Pan, tilt and zoom cameras. So which can pan out. Okay, so we can tilt and also it can zoom. Okay, so if it is a fixed camera, if it is an IP surveillance camera without such capabilities, so if the person at a long distance, the face region is very small, so the facial features will not be clearly visible, so that we cannot identify whom she is or whom he is. But if you could able to zoom out with certain resolution, we can identify the person. That is what the advantage of this particular PTZ cameras. Then we can have this human detection framework, which can be used for, I'll tell you. So one application for this human detection is the people counting. Okay, so the people counting. So we can, generally, traditionally, we have certain logbooks in front of the stores where they will mark out the in time as well as the out time. Okay, so they need to have the count of the customers visiting the shop on that particular day. So without such system, if a person is, so for example, we have the project works like IR sensors. Okay, so IR sensors, when the person is, so when it is fixed in the doors, when the person is getting in, the light will be blocked and it will be counted as one. Okay, so that can also be used, but we need some hardware. So usually this since this cameras were installed in the in the stores for surveillance purpose, it can even be used for people counting also. But here, don't think that people counting is quite easy. So so for example, if a single person gets inside the store, then it is quite easy. When two person come to the store, that is holding their hands or moving very closely, then it will identify as a single blob, because they both are connected components, and they'll be identified as a single blob, and instead of getting the count as 2, it will give the count as 1. So we need to do some pre-post processing work, or pre-processing, or some sophisticated algorithms for identifying that it belongs to two persons, and and we can count the particular one. So these are the other applications where it includes perimeter protection or intruder detection. And again, next thing may be the real time, that is perimeter protection or intruder detection is if some person enters into the forbidden zone. The forbidden region or tripwire should be marked. Okay, so the tripwire should be marked, and if person enters that particular forbidden zone, then the alarm can be raised. So in case of this railway track, or maybe some production region, so where the persons are not allowed, we can identify it. Then another one application, as shown in the second image, that is which we say to be the vandalism. So vandalism is an act that So I think I'll have it. Okay, so I don't have it. Okay. So vandalism is an act that that is damaging some public property. So some people have the habit of scribbling on the walls, so scribbling on the wall, so on. So usually we'll be having a constant background. If the person goes nearer to the wall, and if some changes occurs in the wall after he moves away, then he is called as a vandal. And the activity what has been is an so it has to be reacted immediately. So another one, so as the topic indicates, it is for behavior analysis. So the application includes the elderly home assistant, instant assistance and prevention, then suspicious detection events, the customer behavior detection module, and maybe the pedestrian and traffic flow analysis. So pedestrian flow management, traffic flow management, or allows. So here we can have the algorithm. So one thing I have to mention here is, for although here the people are involved, can the algorithm that we adopt for people counting can be used for crowd analysis? Yes. Can the algorithm that we are using for people counting can be used for this crowd analysis? No, it cannot be. There the features are different, here the features are different. Okay, so here we have to identify the person. So if everyone are moving in one direction, and if something happens in the reverse direction, that is considered as the abnormal event. So here the total flow analysis has to be done for extracting the abnormality detection. Then another thing is including flame detection or video defogging, then motion detection, missing or left object detection, which is nothing but abandoned object detection. It is one of the important application that's related to the public safety. So which means that if we need to go in one that is if some people comes and if we keep a bag in a railway station or in schools, and he will left without taking the bag, then so really it is a potential threat. Okay, so everyone hesitates to go there and open the bag there. Then we have the loitering detection. Another thing we have is loitering detection. Loitering detection means that it is so although it seems that it is very very simple task, simple thing, it is very very difficult to identify whether he is a true loiter or not. Loitering generally means that if a person stays in a particular place without doing any activity, he or she is called as a loiterer. Okay, so he has to remain in certain place without doing any activity. He is called as a loiter. Okay, so why this loitering is an important thing. So if for example the persons in the railway station, consider a scenario of a person in a railway station or in some transit regions. So there may be some actions like smuggling action or some theft action may occur. So it will not happen in 1 minute or 2 minutes or 10 minutes. Okay, so actually these people will go around this transit regions, and they will be monitoring the situations there. And they'll just learn what the scenario is. Then only they can execute their plan. So this is one case. Second case is someone is staying there for a long, waiting for their friend to come, then that is also considered as a loiter. So here we need, it is very very essential. So although these two peoples are identified as loiter, then we need to identify which is normal and which is abnormal. Okay, so we can identify the person with their face movements, with their eyes. Okay, so how they are interacting with the person. So by this we can identify whether he is about to execute certain abnormal plans or not. Okay, so these are some of the potential applications. That is gender detection, face detection, so on. So when you see this gender detection, so there may be certain regions, gender specific regions, and so where the other gender people will not be allowed, so it will block the person. Another thing is, we can also have some age estimation. Yes, so in certain bars, if the person above 18 were allowed, if we are having some regression task for identifying the age, then the people below 18 can be avoided there, automatically blocked there. Okay, so this is the first part where I have just told you about what is video surveillance and some applications with video surveillance. Any clarifications in this part? Because in the second part, we can see about the processing steps involved. Any clarifications or doubts? Has another parameter, that is f of x comma y comma t. So x comma y, it corresponds to the spatial coordinates, and t, which is nothing but the temporal coordinate. So t corresponds to the temporal coordinate. So if we need to process a video, we need to process in terms of frames. So nowadays the video is coming at the range of 20 frames per second to 30 frames per second. So which means that we need to process at 1 second. For 1 second, we will be getting 30 frames. At the utmost case, we'll get 30 frames. So that is nothing but we need to process 30 images. Okay, so we need to process 30 images. And so in this 30, so this corresponds to, when you see this location, this corresponds to 1, 1, 1, which is the spatial coordinate of 1, 1 of my first frame. And this corresponds to 1, 1, 2. And this corresponds to 1, 1, 3, so on. Okay. And coming to the second pixel, this corresponds to 1, 2, 1. And this corresponds to 1, 2, 2, so on. Okay. So for certain application, which is not that much sensitive, it is enough to have 4 frames per second for processing. Okay, but in certain, if the changes in the subsequent frames are that need to be noted, okay, so then all the 30 frames need to be processed. Okay, and another thing, keep in mind that so in the subsequent frames, the changes will not be that much explicitly seen. Okay, so because in a second, so our eye has the capability to, so although there are some discrete values that we are getting in our video, so eye has the perception to make it to be a continuous. So our frames that we are taking, that number of frames that we are taking should not, should gives you the continuous effect, not the discrete thing. So we must be very, choosing the frame rate depending upon the applications that we have. And so now the processing steps, first step includes that background subtraction. So background subtraction involves that is, so as I have told you, when if you are processing 30 frames per second, it is not needed to process all the 30 frames. Okay, so and also we need to process only the changes occurs. Okay, so we need to process only the changes occurs in the subsequent frames. Okay, so for detecting the changes, we need to identify the foreground object or moving objects. That is done by the background subtraction. Okay, the identification of moving objects is done by the background subtraction. And second comes the object classification. So when if we are identifying the background objects, that is the foreground moving objects, all the foreground objects will be identified. So for example, the foreground may be, so it may be, we can say that, so if you are interested in detecting a person who is walking in the road, pedestrian, then actually the vehicles which is moving will all be detected, and also the person will also be detected. So we need to classify. If you are going for a human behavior framework, then the vehicle need not be, doesn't play an important role. So we need to classify the vehicle from the moving objects. So that is the vehicles from the pedestrian. So we need to classify the objects there. And then there's a third step. So here, since in case of a video, we need to track the person in the subsequent frame. How he is behaving in subsequent frames need to be tracked. Okay, so that is x comma y in your first second. Likewise, we need to be tracked, and then after tracking, we can analyze the behavior or activity of the person. So these are the different frameworks that we have. So now let me brief each and every one with some examples. So coming to this background subtraction, object segmentation, or we can have it by another name as foreground detection also. As foreground detection. See here, the thing is, we need to detect the moving objects. So the discriminating moving objects from the background scene is called the background subtraction. So here I'll tell you few things. The first one is the things will be different if it is a static camera, and if it will be different in case of a dynamic camera. Okay, so what is a static camera? So when you see a static camera, the camera is fixed. That is for video surveillance purpose. Your camera will be fixed. Okay, so which is called as a static one. And dynamic camera. So here your background region will be fixed. Okay, so when you see the static camera, your background is fixed, and only the moving objects will be changing. Okay, so only the moving objects will be changing. But when you see this dynamic framework, so assume that the camera is placed in a trolley and it is made to analyze a moving person. So in such framework, what happens? The camera is moving and also the image is moving. So here it is the scenario or algorithm that we need to adapt for the static environment as well as the dynamic environment will be different. Okay, so the scenario that is for setting the static environment as well as the dynamic environment will be different here. And the challenge here in designing a background subtraction technique should be it must adapt to the illumination changes, and it may be illumination changes means, okay, so I'll tell you one case. So for example, since here we are talking in brief about the static camera video surveillance application, it is very easy to get the frame without any moving object. Do you agree with me? So that is for example, if I need to monitor my classroom, I can fix a camera there, and the background is nothing but only the benches, and the benches as well as the desk were there, but and also the walls with fans etc. can be there, but without any students. Okay, so before 9 o'clock, if 9 o'clock the first person enter, before 9 o'clock, if I take a snap of it, so it gives me the background frame. Okay, so if I take a snap, it gives the background frame. Yes, so but in case of dynamic camera, it is very difficult to take such a background frame. Okay, so the illumination changes, it may be okay. So this is one of the thing. Then if you have the motion changes or camera oscillation, it is very difficult to get the background or foreground object. And then if there is a moving background object, so if the moving background object, that is for example, if you are taking a photograph in front of a waving tree, or maybe in case of a seashore, it is very difficult to get the foreground object. Okay, so these are the challenges. And so here we have two conflicting requirement. One is the accuracy, and second one is the fast responsiveness of the model. So here, because since this is the initial step in our video processing, so we must be very careful in getting a good foreground object. So if this foreground object extraction is failed, then the subsequent process will not be correct. Okay, so we must be that is the output that we get must be accurate, and it should be fast. Okay, so since it is a pre-processing step, and if you are using for a real-time environment, getting the moving object itself take 1 minute, then it is useless. Okay, although it may be accurate, it is a useless thing because it cannot be fit for a real time environment. So let us see about the basic processing that is involved here in this background subtraction framework. So that is here we must need, as I have told you, we must need 2 frames. Okay, so here we must need 2 frames. One will be the background frame, or we can say it to be the reference frame. Reference frame must have only background. Okay, so reference frame must have only the background. Okay, so already if we take the snapshot and if we have the reference frame that is represented as f naught of x comma y. Okay, this is nothing but the reference frame. And then we may have it as ft of x comma y. So ft of x comma y indicates the frame at time t 1 second. Okay, so or we can say at the for not maybe 1 second, or the first frame, second frame, third frame, so on. So otherwise this can be represented as f of x comma y comma t. Okay, so this t is indicating the number of frames. Okay, so t minus 1, so it can be t plus 1, t plus 2, etc. So what we can do is, when the simple mathematical operation that we can take here is the subtraction of the 2 frames. Okay, so in this example, this we have it to be the that is the reference frame that is represented as f naught of x comma y, and this is the current frame that is represented as ft of x comma y. When you subtract these 2 frames, you will get this frame. Yes. So will it be black and white or some other colors? If I subtract this 2, so when you see these 2 frames, it is taken, the backgrounds are the same. Only difference is these 2 human were walking. Okay, so now when you come to this equation, it doesn't take only the difference, but also here we are having an absolute value. Okay, so it can be a square, we can take the square, or we can have the absolute value. The reason is, so we are interested to denote only the difference. Excuse me, ma'am, for 1 minute.
Yes, ma'am.
Okay, so we are not interested in getting the actual difference. That is, whether it may be it may be. Okay, so whether the difference may be the positive or it may be negative. So we need to identify whether there some changes happens. Okay, so that is why we are taking the absolute value. Else we can take the square value also. And then what can be done is, so what it will give the pixels in some gray levels. Okay, so for getting the binary value, we need to apply a threshold. So what this threshold indicates is, so for example, we can fix a threshold value and we can say that if the value exceeds the threshold, it can be marked as 1, and if it is below the threshold, it can be marked as 0. Okay, so that's why we get a binary image. Okay, so that's why we get a binary image. And so the simple difference of the two images followed by thresholding will give the moving objects. And so here another important challenge is how to fix the value of threshold. Okay, so if you are fixing the value of threshold as high value, okay, so if the threshold, fixing of threshold is high, then what actually happens is even the background objects will not be classified, or even the foreground objects will not be identified. Okay, so since we are if we are fixing it very high, if the difference is very less, so it will not be detected. And if the value is very low, then what will happen is background objects will also be classified as foreground objects. Background also will be classified as foreground. Okay, so these are the two drawbacks that we have while when we are fixing the threshold value. And another thing that although it seems to be a simple thing, so here when we are taking the difference, so taking the difference here, not only the person but some additional informations were also visible. So this additional information, it is due to the shadow present. Okay, it is due to the shadowing effect. So we need to tackle the shadows also for getting the good output. And so another one important point here is, if the same background that we have taken, so for example, if I'm monitoring the happenings by 9 o'clock, and if I'm starting my monitoring from 9 o'clock till 4 o'clock, and if I have a background frame taken at, or rather that is the reference frame f naught of x comma y taken at 9 a.m., can be used, the same background frame, can it be used for this 4 p.m. also? Okay, if the same frame can be used for 4 p.m. also, it cannot be, because the illumination variations will be there. Okay, so illumination variations will be there. So at certain duration, not often, but we have to update the background model. Okay, so here the background, it is not fixed. So it is not, in the previous case, it is mentioned as f naught of x comma y, but here it is not f naught of x comma y, it need to be varied. Okay, this background model should be updated. So how this background model is updated, depending upon how the foreground is detected and also the previous values. The detection, the values is scaled by certain value of alpha. So it gives the percentage of how much percentage you are taking the current frame and how much percentage you are taking your previous frame. So when the alpha value is equal to 0.5, then indicates that you are taking the equal shades. So if it is greater, one is greater, another is less, which indicates that how much percentage, how much importance that we are giving to the foreground as well as the other background models. So this is what the background updation results. So it is affected by noise, illumination variations, and cannot adapt to the change in the background values. So, and another thing here is, so instead of considering a single frame, so previously what I have told is, we can consider a single frame. Okay, so if there is some noise in the single frame, that will be affected. Okay, so if there is some noise in the single frame, it will be affected. So instead of considering a single frame, okay, we can consider multiple frames. We can consider multiple frames for getting the background model. Okay, so instead of having one frame, we are taking multiple frames. Okay, so but from this multiple frames, we need to get the reference frame f naught of x comma y. So how we can get this frame is, see, although if we are considering some 25 frames, Okay, if you're considering 25 frames, we can take the median, value, the statistical parameter, mode value, or we can calculate the mean value. Okay, so I'll tell the importance of taking all these parameters. See, if I take my first pixel, that is at location 1, 1, the pixel at the location 1, 1, it may be for your first frame, that is f of 1, 1, 1. Then the second one will be f of 1, 1, 2. Then third one will be f of 1, 1, 3. So if you're considering some 25 frames, it will be 1, 1, 25. Okay, so we can, from this, so you'll get 25 pixels here. Okay, so just you thread out all the pixels. Okay, you'll get it will be represented as a one dimension. It is represented as I can say it as a vector. So from the vector, you can take any one of the parameter, either it may be a mean value or median value or a mode value, and that is represented as the first, that is the pixel of the background model. Okay, that is the first pixel of the background model. Now, so what is the importance of taking the mean? So if you are all the statistical parameters, so if you are taking the that is the mean value, what actually will happen is, so uh, if there is some noise present, okay, so it will just smoothen your signal. Okay, so for example, if my pixel values are almost in the range of 20 to 30, but there is one pixel value that corresponds to 100, okay, and unknowingly, if I take that frame to be the current, that is the foreground or background frame, so it will corrupt the entire system. So in such scenario, if I take the mean of that 100, that is 25 frames, if that one pixel is 100, so it will smoothen out and it will bring into the range of the remaining pixels. Okay, so this is one the advantage of using the mean. So similarly, median, it will arrange in order and it will take the center pixel. Mode, it will give the most repeating values. Okay, so these parameters can be used for designing the background model. This is one example. So we can have, let me brief about what are the other techniques that we have here. So the technique what I have explained here is the temporal differencing. Okay, so the technique what I have explained here is nothing but the temporal differencing. Another background subtraction can be a frame to frame difference, or maybe a simple background subtraction model or adaptive background subtraction model. So the second scenario what I have told is nothing but when the camera is moving and also the object is moving, it is very difficult to get the current frame. So in such scenario, we have to take the motion vector. It is dictated by this optical flow. Okay, it is dictated by the optical flow. So optical flow says you how the images are moving. It gives you the vectors. It gives the motion vectors along x direction as well as along the y direction. Okay, so it will give you how much it moves along x and how much it moves along y. So nowadays, in all the processes, the deep learning plays a very important role, and here too, in even starting from the background subtraction till the end, the this particular deep learning plays an important role. So the foreground detection with deeply learned multi-scale spatial temporal features, just I'll give you a clue how it can be used. So this is what the framework, and in this framework, here it is represented as A-truss convolution. Okay, when you see the block diagram, where we have A-truss convolution, another one 3D convolutions, and another one we have is deconvolutions as well as the sigmoid layers. So, so we know convolution layers. When in case of a deep learning framework, we'll have the convolution layer, batch normalization layer, activation layers, etc. Okay, so since where we have the convolutions which can be done for the signal, can be done for the image, where we'll be having 2D convolutions. So since it is a video, we have the 3D convolutions. So 3D convolutions, where which needs to operate on the 3-dimensional space, where the third space is which is will be the temporal one. And here we have another type of convolution called as atrus convolution, which is also called as a dilated convolution. So in case of the foreground detection framework, the input image size as well as the output image size should be the same. Okay, the input image size as well as the output image size should be the same. So in such scenario, we need to reconstruct back with the help of deconvolution layers. Okay, so with the help of deconvolution layers, we need to get back our original image, where the size of your output should be equal to the size of the input. So the foreground detection using D features, it is a dual multi-scale 3D fully convolution neural network for foreground detection model, and it uses encoder-decoder structure to establish a mapping from the image sequences to pixel level classification. So here in this paper, they have taken a total of 16 continuous frames, including one will be the previous frame, one will be the current frame, and the previous 15 frames. So your foreground region is extracted depending upon this 16 frames, considering one current frame and 15 previous frames. And so this encoder, it extracts the multi-scale spatial temporal features from the input sequence, and the decoder merges the features to reconstruct the pixel-wise detection results. Okay, this is one of the examples showing the convolution framework. How the process is done. See, so in this numeric matrix that is displayed here, where we have an image of size or a patch of size 5 cross 5, and the resultant that we are obtaining is only 3 cross 3. So it all depends upon this kernel size. So the image size is 5. The image size is 5. So 5 minus the kernel size is 3 divided by the stride is 1 plus 1. So 5 minus 3 is 2 plus 1. So your output will be of 3 cross 3. So from this, if I need to get back my 5 cross 5 value, then I need to go for padding. Okay, so these are the padded outputs. So these are the padded inputs. So this padding can be either a 0 padding. Okay, this can be either a 0 padding, or it can be a pixel replication. Okay, so it can be either a 0 padding or it can be a pixel replication. So that from 5 cross 5, you are converting it into 7 cross 7. So 7 minus 3 divided by 1 plus 1, you'll get the value as 5 cross 5. Okay. So if they are increasing the stride, also the size will be reduced. So that is 5 minus 3 by 2. So where you will get is 2 by 2, 1 plus 1. So you'll get the output as 2 cross 2 as your output. Okay. And what this atrus convolution is. So atrus convolution, it's when you see the difference between the two. So here, although we are using the pixels of 3 cross 3, okay, so although we are using the kernel size of 3 cross 3, it tries to operate on a 5 cross 5 region, so that with the 3 cross 3, we are analyzing a 5 cross 5 region. That is what this atrus convolution, it is also called as dilation convolution. Okay, so it is one of the main what I can say is main layers when you are working with segmentation like approaches. Okay, so when working with segmentation like approaches, this plays a very, very important role. Okay, so with 3 cross 3, with only the value here is indicated by the block, that is the some shaded values. It is only having some 3 cross 3, but it is playing about 5 cross 5 pixels. Okay, so from 3 cross 3, so what actually happened is from 3 cross 3 values, they are having some upsampling. Okay, so they are inserting some values here so that it is converted to 5 cross 5. The kernel itself will be 5 cross 5. So which is used for increasing the receptive fields. And so this is the reverse of the convolution what has been. So this two type of convolutions we are using in the forward, that is encoder part, and for the decoder part we will be using the transposed convolution. So when you see this transposed convolution, the resultant obtained here will be only 2 cross 2 pixels. From this 2 cross 2 pixels, we have to get back into 7 cross 7 by the interpolation techniques. So this is what the thing is. See, for if we have, this is one good example. If the input is 2401, okay, so it is of size 2 cross 2, and so the input of size 2 cross 2 as well as the convolution is of size 2 cross 2. But we need to get the output of size 2 cross 2. We need to get the output of size 3 cross 3. So in such situations, how this is handled is, we have to first frame the 3 cross 3 pixel value, and all the samples in this matrix has to be multiplied by the value of 3. So 3 into 2, you'll get a 6. 4 into 3, then, sorry. So I have to multiply by the value of 2 here. Okay, so 2 here. So I'll get a 6, then 2, then I'll get the value as 2. Okay, then I'll get the value as 10. Okay, so this is by obtaining, multiplying 311315 with the value of 2. And second one, you have to multiply this with the value of 4. So if you're multiplying by the value of 4, you have to replace at the later end. So I'll get as 12, 4, 1 as well as 20. Similarly, you multiply with 0 and this. So now you have to add it out. Okay, so when you see the first column, here I have 6, here I have no entries, here no entry and no entry. So I'll get the output is 6. So next here I have 2 plus 2 plus 12 plus 0. So I'll get the value as 14. And next is 0 plus 4 plus 0. I'll get the value as 4. So likewise, this is what the concept there in transposed convolution. Okay, so this is 3D convolution. So 3D convolution is, instead of working on a 2D space, it tries to work with a 3D volume of data, which is having x, y as well as its depth. Okay, so which is having the values of x, y as well as its depth. Okay, so I have to, as I have mentioned here, so we will be using, so just I'll explain the concept how this process is being happening. This A-trace convolution, 3D convolution. So here, as I mentioned previously, it accepts 16 frames. Okay, so the 16 frames were given to the 3D convolution layer. So this is what the size, the number of frames, its height, width, and 3. 3 here indicates the number of, it is a color image. So your color image will have red, green as well as blue plane. So it is represented as H, W, 3. And so we are using a 3D convolution. Here that is 3D convolution layers, and it is used with the max pooling. Okay, so it is used with max pooling layers. So if max pooling layers, it tries to downsample the size of the image. Okay, so here totally 16 filters, 64 filters are used. So I'm getting the values of 16. No temporal pooling is done. So all the 16 frames will be there, followed by the size of the frame is reduced to H by 2, W by 2, as well as we'll get 64 feature map since we are using 64 filters. And then finally, here the value is 1. So there is no downsampling, only the spatial downsampling happens. And second one, here again, the downsampling of the frames, number of frames occurs. So from 16, we are getting the value as 8. Then again the downsampling of the images, you get the value of H by 4, W by 4, and the totally 128 feature maps. Then here again downsampling by 2, so it is 4, H by 8 as well as 256. So this is what. Finally, we are trying to make it into 1, H by 32, W by 32, 512. Similarly, here the A-trace convolution, the same scenario is followed, and here too we get a only one feature map with reduced sizes obtained. Okay, so for example, if we give the image of size some 512 cross 512, 512 divided by 32 will be the feature size here. But we'll get 512 feature maps since we are using 512. That is 512. I can say that convolution. That is convolutions. Convolution filters are used, so you'll get us 512 feature maps. Similarly, when you see this scenario, this is what the first scenario. Here, the interframes were considered. Okay, so where we are having not the single frame, the difference between the subsequent frames were considered. So where which will be I minus IT minus 14, IT minus 12. Okay, so the difference in the subsequent frames of are taken to study how the motion has happened in the subsequent frames. And here too, we are running through the procedures of 3D convolutions. The same thing, and here too we get the value of 1 H by 16, H by 16, W by 16. So total the size obtained by these layers will be greater than the size obtained by this layers because it is reduced to 32. So now what we need to do is we have to take this to a decoder and we have to do deconvolution so that only it can be merged with the feature maps obtained in the encoder part of the second stream. It is C from H by 16. Here it is also your from H by 32. It is changed to H by 16, and from H by 16 it is changed to H by 8, H by 4, H by 2, and finally it is converted to H. So after converting to H, we are using some sigmoid classifier to get a binary mask. Okay, so by using deep learning framework also, we can do the same process. When you compare these two things, so deep learning frameworks, the time consuming is very great, larger compared to that of the frame subtraction model. So if you need high accuracy and if time is not the constraint, in such application, you can use the deep learning based approach, and if not, you can go with the other one. Okay, so these are some of the results. And so you can use this link for getting the recent papers, recent background subtraction papers. And when moving to the recent papers it all concentrates on if only it is a challenges will be posed now and then for doing the background subtraction. And when you see this background subtraction frameworks, so usually it will have deep learning based frameworks now for change detection, then spatio-temporal augmentation, then some recurrent networks and also GANs were used nowadays. So these are some of the databases that you can use if you are working with background subtraction alone. Scene ChangeNet, Scene Background Modeling, SBI, SBM. So these are some of the databases. So any doubts or clarifications?
Participants can unmute yourself and ask.
Any clarifications?
I think no, ma'am.
Okay, ma'am. Then I'll proceed further.
Yes, ma'am. Thank you.
Okay. Okay. So now the next is, ma'am.
Good morning.
Tell me, ma'am.
Yes, ma'am.
Ma'am, actually, I'm Kavita Sendil. I'm assistant professor from MAM College of Engineering and Technology.
Okay, ma'am.
Actually, ma'am, I thought of asking a question, but After finishing the entire presentation, let me ask so that it would be effective for others too.
Okay, ma'am. Okay, ma'am.
Thank you, ma'am. I don't want to disturb you. Thank you so
Okay,
much.
ma'am. Okay, ma'am. Okay. So the next part here is so for object classification, that is since we have extracted all the moving objects, the next thing is we need to classify the objects. The reason for classification is sometimes if you are using the simple frame subtraction model, then what will happen is even some of the leaves, that is moving leaves or waving trees, it will give you a false output. And again, as I have mentioned previously, if you are trying to monitor the pedestrian, other moving objects, moving trucks or moving cars will also be considered as the moving objects. So will also be detected in the foreground thing. So we need to identify, or we need to classify the moving objects. So it can be done with the help of motion-based classification, or it can be done with shape-based classification, or maybe a texture-based classification, or maybe the color-based classification. So the simple representation space, so usually we will be concentrating on the shape-based classification or how it is moving, the motion-based classification. The basic thing is, we have to represent the objects in terms of in terms of either by its centroids of the object. Okay, so after detecting the moving objects, we will be representing it by its bounding box, or maybe by its centroid, or with the help of its bounding box, like a rectangle bounding box, or it may be elliptical bounding box, or it may be a cuboid like this, or even the skeleton can be used to represent. And the articulated object, so human is an articulated object where so he can be he can change his shape, because his body parts are connected by joints. The shape can be changed. That is, if you are standing, the aspect ratio will be different, and if you are sitting, the aspect ratio will be different. So in such case, if you are about to analyze an articulated object, then the skeletons or the blobs can be used. And if it is a deformable objects, so we can use some mathematical modeling for analyzing. One of the important thing that can be used for the pedestrian detection is the histogram of oriented gradients, which we say to be HOG. So I'll tell you the basic things how this HOG can be histogram of oriented gradients can be calculated for getting the for describing a pedestrian, and how it can be served as a feature for classification. So as the name indicates, histogram of oriented gradients, first we need to calculate the gradient of the image. Okay, so the gradient of the image is given by del f, which is equal to the dou f by dou x, and also it is given by dou f by dou y. Okay, so it is the first order difference along x as well as along y. So from which we need to get two parameters. One is the magnitude of del f, which is nothing but root of dou f by dou x the whole square plus dou f by dou y the whole square. Okay, so this gives the magnitude. Another gives you the direction. So which is nothing but tan inverse of dou f by dou y divided by dou f by dou x. Okay, so the two parameters, how much magnitude and how what is the difference magnitude and how it is oriented. Okay, in which direction it is getting oriented, it is given by these two parameters. So for example, if you consider an image of size so this is the rows, so it may be of size 128 cross 64, 128 cross 64, and if you're trying to divide into 16 cross 16 of 15 blocks overlap, that is, for example, if you consider this as this a human, I try to divide this into 16 blocks. Okay, so whatever may be the size of the image, I have to divide the image into 16 cross 16. So one block will have the size of 16 cross 16. And it says that we are allowing 50% overlap. 50% overlap indicates that So if my first block is from 1 to 16, my second block will start from 9 to. Okay, so that is what 50% overlap. So if you are taking this, I'll get some 105 blocks in total, and one block now consists of 16 cross 16 values. Now one block consists of 16 cross 16 values, and in this block I will be dividing it into 2 cross 2 cells. Okay, so 2 cross 2 cells, and with a size of 8 cross 8. So totally I'll get 8 cross 8 cells. Okay, so so I'm again dividing so that I'm getting into 8 cross 8 cells. So 16 cross 16 blocks is divided into 4 8 cross 8 cells. Now, so as I have to mention previously, here we will get when you see an image of size m cross n, the magnitude of del f will also have the size m cross n, as well as the direction of it will also have m cross n. Now, we are trying to quantize the orientation into 9 bins. Okay, so if the orientation of del f is having the values from 0 to 180, we try to divide it 180, then we try to divide it into 9 bins. Okay, so each of dimension or each of width 20. So 0 to 20 degrees will be coming under one bin, and this 21 to 40 will come under the second bin. Likewise, we are trying to divide. So this is one the pictorial representation. Okay. So now we have to. So what the next one is? So we have calculated the gradients. Orientation is also calculated. We need to plot the histogram of it. That is the next step. So for plotting the histogram, we have to quantize the orientation into 9 bins. That is from 0 to 180. We have to get some voting for getting this gradient magnitude. See, as mentioned previously, each of every bin is having the width of 20. That is 0 to 20, then 20 to 40, 60, 80, up to 180. And the important one is the center of the bin. The center of the bin will be 10 degree, and the center of the bin here will be 30 degree, and here it will be 50 degree, 70, then here it will be 90, this is 110, and here we have it is 130. Okay, so for example, if my value of theta is equal to 85, okay, for example, if I have a value of theta is equal to 85, and if my magnitude value corresponding to that theta, so we have two images. Okay, so now we have two separate images. One corresponds to the magnitude, another corresponds to the value of theta. So if my first value of theta is 85 and the magnitude 85 degree, and the magnitude here, for example, it corresponds to some value of 100. Okay, my magnitude is 100 and the corresponding value of theta is 85. Then how we have to, in which bin does this comes is, see, we have to take this 85. Okay, so 85 is between the bin centers of 90 as well as 70. Okay, so if it is 85, okay, now we have to write with respect to the bin centers of 90 as well as 70, where your 85 lies. Okay, and next one is how much weightage that we have to give for the bin center 70, and how much weightage that we have to give for the bin center 90. Okay, so how much weightage of this 100, the magnitude value is 100, in that how much weightage should I give it for 70 bin center, and how much weightage I should give for 90 bin center should be discussed here. See, if it is 85, the difference between 85 as well as 90, it is 5. Similarly, 85 minus 75, it is equal to 15. So 85 is nearer to 90, the difference is 5 rather than 15. Okay, so how we have to give the ratio is 5 by 20. 20 is the total. That is the deviation between the two bin centers is 20. That is 10, 30. So deviation is 20. So that is out of 20, weight 5 is given for 111. The 5 by 20 is given for this 90, and 5 by 15 by 20 into 100, it is given for the second one, which is for 70. Okay, so this is how we can 3 by 4th of the value will be assigned for your 70 value, and 1 by 4 will be assigned for the other case. Okay, so this is how we can assign for the bin centers. So totally the feature vector in this previous example will be, the feature vectors will be, since the size number of blocks that we got is 105. So in this 105 is again divided into 4, and in this for every 4 we are getting 9 feature values. So here totally for an image we will get 3780 feature vectors. Okay, so this is how a histogram is visualized. So if you are visualizing a histogram, it seems to be like this. How much each and every pixel is oriented. Okay, so this is how it is oriented. How the head regions. So we can say take the shape of the object from this representation. Okay, so this is what the second important step that we have discussed is about the object recognition task. So object classification task. So after object classification, we need to track the objects. Okay, so if you are interested in pedestrian, we need to track the pedestrians across the consecutive frames. Okay, so in video object tracking, the objective is to locate one or multiple objects of interest in each frame. So here if we need to locate one or multiple objects, then actually the problem here is the background subtraction result should be good. Okay, so otherwise, instead of locating 2 people, it may be say giving the track of the single person. So if 2 persons are walking close by, then it will identify it as a single person and it will give the false results. Okay, so in order to avoid that, your background subtraction algorithm should be good. So it is the problem of determining the position and other relevant information of objects in the image sequences. Okay, so this object tracking, it aims at determining the trajectory over time, or in certain cases the trajectory of the camera itself. So how it can be done is, so for example, if the object, so we have to, after your background subtraction, and if the person is detected, we need to locate the person. So locate the person, and if the centroid of the person is located at x comma y in the first frame, and in the second frame if he is located at x1 comma y1. Okay, so if you join these two, if you are taking a separate frame, and if you are joining x1 xy and x1 comma y1, if you are joining these two locations, then it gives the trajectory of the person. So one technique, so there are 2 approaches in object tracking technique. So in one technique, we can detect the object and we can get the correspondence location. That is, so in the first frame, you have to locate where the person 1 is identified. And in the second frame, you have to locate where the person is identified. Then where the same person is identified. In the first frame, so these are the certain challenges in case of your object tracking mechanism. So maybe in the first camera, maybe you are detecting in the first frame, for example, you are detecting person 1. There is only one person and I am detecting one person, and in the second frame the person 1 moves, and here a second person P2 enters. This should not be corresponding to, this should correspond to person 1, and this should not be corresponding to person 2. Okay, so in the first frame, if you are linking the location x1, y1, and here also if you are locating x11, y11, that should be located. But if you are locating x12 and y12, if you are linking this two, it is mere wrong. Okay, so one mechanism that is adopted is we have to detect each and every objects in the subsequent frames, and then the trajectory can be marked. And second approach can be we can predict the location. So for example, if a person is present in the location of x1 comma y1, there may be two possibilities. It may be some affine transformation can happen, and there may be a slight change when coming to the second frame. So we can go by prediction based approach also. So the tracking, what may be the possible tracking outputs? The tracking output can be the contour of the object, or the 2D image coordinates of the center of the mask, its 3D position in the real world, or the joint angle, so on. Okay, so if we see the trajectory of a person itself, we can identify whether his movement is normal movement or abnormal movement. So in the first in the first one, the trajectory here, we may say that the person is moving moving in this direction in a straight path, but here it is taking some zigzag paths here. So here too some zigzag path at this location. So but here this is a good path where he is moving from here till there. Okay, so but here one such rotations as one such he has moved only once. So from this, if you are analyzing the trajectory of a person itself, we can identify what kind of movement he exhibits. Then the challenges in tracking is the changes in the appearance of the object with viewpoints, illumination, as well as the possible articulation. So if you are coming with multiple cameras, even with a single camera, if the person is viewed at one angle, and if he is rotating by certain degrees, and if he is moving, the viewpoint will change. And also another thing is the illumination, if it's get changed, and if he is having the possible articulation, that is, so if he is moving without any carried baggage, and if he is carrying certain baggage, then automatically the structure will be getting changed. Okay, so it is very difficult to track. So it may say that it is different object and gives the false result. Then partial occlusion of the target bodies. So for example, if a person is moving and if he is coming back of a pillar, then the part of the body will be visible and the remaining body will not be visible. So that is what partial occlusion. And in addition, it is difficult to maintain the identity of the pedestrian during the tracking when they are close to each other. So for example, if there are two persons, as I mentioned previously, so if there are two persons, the first case, the person will be the person, if you are labeling it as P1. In the second frame, the person, if two persons are there, the person 1 should be labeled as person 1, and the new entry has to be labeled as P2. Okay, if there is certain mismatch or feature matching, so abnormalities, or it is merely we cannot go further process in activity recognition. So this is one example which shows the partial occlusion, and here this example shows the scale change. The same vehicle, as it is far away from the camera, at frame 1, it is far away from the camera. Its size is very small. So where we say the scale change occurs, and when it is nearing to the nearing to the camera, the scale is getting changed, but here the front view of the vehicle is visible at frame 1, but at frame 252, the side part of the vehicle is visible. So kindly go through this challenges in tracking as I mentioned. In the first frame, 2 persons were detected and they are identified as 2 different persons. So person 1 is given by red color and second person is given by a blue color bounding box. And when both came together, it is identified as a, because as we have seen here, it may be identified as a single blob and the features doesn't match either with person 1 or with person 2. So it is given as person 3, it is marked as a green color blob. Okay, and then so these 2 people had some conversation and they are departing. So in the third frame, it is correctly given. And in the fourth frame, what happens? These 2 persons, they are again merging together. It is identified by green color, that is the third person. And in the fifth frame, only the person 1, he is displayed with different viewpoint, showing his backside to the camera. So in such case, again, it is misclassified as a third person, but it should be identified as person 1. His feature may be matching more with the third person, so it is matched with the third one. And finally, as they depart, it is given by 2 different colors. Then what are the representations of the object tracking? So the object tracking can be done with the help by representing a single point as I have shown previously, that the centroid of the objects can be used. So otherwise what you can do is we can take some random points and those points can be tracked. Okay, so for the first point, how it is changing in the subsequent frames can be tracked. So otherwise what can be done is we can give it by some bounding box, and that bounding box, it is a rectangular bounding box and that can be tracked, or else elliptical bounding box. Elliptical bounding box is usually preferred because so it will be somewhat compact corresponding to that of the rectangular, so it can be used. And the first row, last case, where the body regions, the head region, torso region, then the hand, upper hand region, lower hand region. So these regions were identified and it can be tracked, or else we can take the skeleton of the object or the contour, the points around the contour of the objects, or the entire contour or the shill out of the objects can be used for tracking. So this is so as given in the diagram as images. So this gives the points. It is represented by point, that is a centroid, or by a set of points suitable for tracking object that occupy small regions in the image, or the object shape is represented by rectangle, ellipse, etc. Or object shill outs or contours, that is the contour which is the boundary of the object, shill out which is the region inside. Okay, so this is the contour and the region inside we say to be a shill out. So it may be a shape-based methods, motion-based methods, or maybe a part-based methods. So so one issue that I have told is the partial occlusion. So partial occlusion means partial hiding. Okay, so some part, if I'm moving back of a pillar, some of my body parts may be hidden from the viewpoint. So in such case, instead of modeling the entire human, we can use some body parts like hand region, leg region, etc. So by using this body parts, we can track the objects. So this tracking mechanism can be of region-based tracking, or maybe of contour-based tracking, or feature-based tracking, or model-based tracking. Finally, we can combine all this and get the hybrid tracking methods. So the region-based tracking algorithms track the objects according to the variations of the image regions. So corresponding to the moving objects. So here in case of region-based tracking algorithm, it may be the color of the objects used for tracking. For example, we can track the objects depending upon their shirt color or maybe the luggage that he is handling. Likewise, so depending upon a region, we can track the objects. And in contour, instead of tracking the whole set, track only the contour of the objects. The external boundary of the object is marked and we can track the objects. And feature, certain feature points were extracted from the image and that feature points can be tracked. So here in case, for example, if you want to go for expression analysis or emotion analysis, we can, instead of analyzing entire face region, we can analyze the fiducial points of the image and that can be tracked in the subsequent. So we have Harris corner detectors. The Harris corner detector is effective in detecting the feature points, and this feature points can be given to a KLT algorithm. KLT algorithm is Canada-Lucas algorithm, and when it is given to this algorithm, it will identify how the feature points is moved in the subsequent frames, and we can identify the tracking. So in case of model-based tracking, it involves three main tasks, which we need to construct the human-based models and the representation of priori knowledge of motion models and motion constraints and the prediction of search strategies. And also traditionally the geometric structure of human body can be represented in four styles. Either it can be a stick figure or maybe a 2D contour or volumetric model or maybe a hierarchical model. So the hybrid tracking is simple, where we can combine two or more approaches for getting the tracking. So either we can combine either region-based or feature-based tracking, or we can combine the region-based or feature-based tracking. So for getting some good results. So another one tracking method that found to be quite interesting is the mean shift tracking method. So it chooses the feature distribution to represent an object, and it starts with, I'll show you with an example. So for example, if I need to track, okay, so in this example, if I need to get the region which is having high density, automatically our eyes goes to this particular region, isn't? Our eyes will go to this particular region. So this is how it is done as, first, we need to identify any random region of interest. Okay, we need to identify any random region of interest, and then we need to calculate its center of the mask. Okay, if you are identifying the random region of interest, it will have its own center. Okay, the region has its own center, and then we need to have to calculate the center of the mask. Okay, center of the mass in this region. So this particular region is more denser compared to this region. So this is what the center of the mask of this particular circle. Now the difference in the actual center is given by the difference between blue color as well as a yellow color. Okay, now what it will try to do is, the algorithm name is mean shift. Okay, now the mean will be shifted to the center of the mass regions. Okay, so it will try to, this is the mean shift vector. Now it will be shifted to this particular location. Okay, now again it has to go for the second iteration. Next it finds, so this will be the denser region. Now this is my mass. Okay, and this is the denser region. So I need to calculate the center of the mass now, and then mean shift vector, it will move. Okay, then again the center of the mass, mean shift vector, it should move. Okay, and then it doesn't. So this may be the, as we have identified, this is the densest region has been identified. So here we have a mean shift vector. So mean shift vector, it is given by, this may be your center point, and this is the mean vector as we calculate with the help of your data points. Okay, so difference between the two will be the vector that we need to move. How it can be used for object tracking. Okay, this is a general object tracking mechanism how it can be used for object tracking is, so we have to choose a reference target model, and we can use any feature space. The feature space may be a texture feature space or color feature space, whatever it is, we need to choose the feature space, and we have to represent the model by its PDF, and then we'll be having the target candidate, and we have to find where it matches, and this target candidate may be a next frame. Where it matches will be that center location. So some similarity function is calculated to get the difference, and we can identify that this is what the location change happened. So the starting from the current window location, the mean shift algorithm will find a new peak or mode of the feature distribution, which is centered over the object that produced the color and texture in the first place. So in this case, the mean shift window tracks the movement of the object frame by frame. So you can please have a look on it. So these are the few of the, so this link I have given few recent papers and data sets available for the purpose of object tracking. So these are few of things. CIFAR10 ImageNet. So this is for image classification problem. I think next part will be the activity recognition. So where I'll be covering two activities. One is for face recognition task. Another may be for activity recognition. I think I have 10 more minutes, and so I can take up the questions now. And if time permits, I'll move to the next part.
Okay, ma'am.
So any clarifications?
Participants, so far, if you have any doubts, you can clarify. Ma'am, if you want break after 2 minutes, you can continue, ma'am. Or else you can continue now.
Okay, ma'am. Okay.
Thank you, ma'am.
So because if I start with that, it will take much time. Okay, at least I try to complete any one of the applications, and in the afternoon class, let me continue with that, the second applications, and then I may have it some hands-on with that is background subtraction tracking, etc.
Yes, ma'am. Yes, ma'am.
Okay. So when coming to this activity analysis, so here I thought of explaining two things, one with emotion recognition and another with activity analysis in general, action recognition in general. So for emotion recognition, so we need to locate the human faces in the image, regardless of their position, scale, orientation, pose, and illumination. And then we need to find the emotions that they are displaying. And so for face detection, as that of it is a pre-processing, that is in case of a real image or a general scenario that is given, we need to detect the face regions. So here it may be of two approaches. One may be a sliding window approach, that is a template face will be given, and it can be slided over to the entire image, and where the face region matches, we can say that where the template matches with the current frame region, then we can say that this is what the location, the the phase region is located. This is one thing. And second, it can be a feature, it can be either the entire region or maybe the interest point descriptor. So where from the input image, we have to extract the interest points, and this interest points need to be matched and has to be carried on. And the next one will be the tiny phases. So tiny phases is based upon the deep learning based approach. Usually when you see this phase detection framework, the most popular one used is by using the Adabus classifier, which is called as Viola-Jones Adabus classifier. So it could, so it's when you are taking the trained model that we have it in MATLAB, it can detect only the phase of size 24 cross 24. Okay, so if the phase region is of size 24 cross 24, it could able to detect. But if the phase region is smaller than that, it finds it's very difficult to identify. That is what here comes the tiny phase model. Okay, so the tiny phase model is nothing but it can detect even a small sized images. So why this tiny phase plays an important role in surveillance? So usually in case of surveillance cameras, all the images were there in long shot, where the scenario is much more explicitly seen compared to that of the human there. Okay, so since the camera is fixed at a certain height, the entire scenario will be seen, whereas the face region is seen a small region of the face will be displayed. So what can be done here is, Viola-Jones algorithm sometimes fail to detect this tiny face regions. So to get even this tiny face regions, we can adopt this algorithm. So this algorithm will have the capability by using the scale varying, it can detect all the regions. So this is the sample outline of detecting faces using a sliding window. So we can manually crop the faces. In training phase, we can manually crop the faces. We can extract the feature from the faces like colors, textures, its contours, etc. And the test image will consist of both the face region as well as the non-face regions. So we have to extract the face regions by traversing this window over to the entire image frame, and we have to match the features. Okay, and we can say whether it belongs to the face region or not. So apart from that, we can extract the interest points. The interest points is represented feature representation, and it is represented in terms of code book. So rather than in the previous case, I have mentioned it about extracting the contours and all. Instead here we can use some feature points and we can use for the calculation. So in case of Adabus Viola-Jones algorithm, they uses some HAR features and then the integral image and additional cascade, where the HAR features are significant in extracting the regions of the face, like nose region, that is the important regions, distinguishing regions of the face like eyes, nose, as well as the lip regions. And also we have an integral image. I'll show how to calculate this integral image. So there are some of the filters used to calculate the image features in the face region. So this is they are some of, so here it is having the value as 1 and this may be having the value as 0. So if I place this region over, if I place this mask over this region, so here this pixels will be multiplied, the content of this pixels will be multiplied by 1 and this regions will be multiplied by 0 and it has to be added out. Similarly, likewise these are the various rectangular filters. The rectangular feature values will be equal to the summation of pixels in the white region minus the summation of pixels in the shaded region. So here, for example, if I'm placing the mask here, if I'm placing my mask here, then my value will be, so this is having, for example, this is having the white region and this is having the shaded region. I'll get 8 plus 7 minus 0 plus 1. Okay, so that will be the feature vector. So the so here some filters, rectangular filters that are used for getting the facial features, for detecting the eye regions, detecting the nose regions, and for detecting the mouth regions. And boosting for the face detection. And so we can make a classification here. So if this region is, if the resultant from the first filter, if it is greater than certain value, then we can give the weight as 1. If it is less than certain values, we can give the weight as -1. Okay, this is how every classifier is framed. So it gives a value of 1 if PT of FT of X is less than the threshold. So else we can get the value to be equal to -1. So you can use certain cascade of certain cascade of weak classifiers to build a strong classifier. Then how to build up the integral image? For building up the integral image, so it is integral. The word itself, it means that it is continuous summation. So for first one, I'll get as 38. Okay, so here I'll get, for the first one, I'll get 38. And the second pixel is obtained by the total summation from the corner. That is 38 plus 66. And the third one will be 38 plus 66 plus 17. This is how it is framed. 38, and second one will be 104. Then 104 plus 17, I'll get as 121. And for getting this one, it will be 38 plus, for this location, it is 38 plus 89. For getting the value at this location, it will be 38 plus 66 plus 89 plus 97. So which gets a value of 290. Okay, this is how it is calculated. You can check the values. So, so we have to initially, your entire face region will be given. We can use some simple features to reject sub windows. Okay, so so it is also window based processing. So in the first cases, we can reject certain sub windows having the values which is which corresponds to non-face region. So initially, if you are giving with 100 windows, maybe 1, 2 or 3 windows may be having the face region, and remaining windows can be rejected. Okay, so in the first step, some 20 windows can be rejected. In the second step, maybe another 10 or 20 windows. And so in the initial stages, we can use some low-level features, and in the higher stages, as we are cascading the higher regions, we can use some good classifiers for getting the resultant. But as mentioned, cases. Okay, so when the face region is very small, it will fail to classify. So in such case, we can go for some deep learning based approach for multitask modeling of the scales. So one thing that can be done is we can have a fixed template. Okay, so as pointed here, we can have a fixed template. Okay, so your template is fixed. And here we can scale down your image by using the pyramidal decomposition. That is, if I have the image of size 256 cross 256, I'll match the image. If my template is cross 16 cross 16, I'll match the 16 with 256 cross 256. Then I'll scale down to 128 cross 128. Then I'll find the match. Then I'll get the matching by 64 cross 64. Then I'll get the match. Likewise, I'll be scale it down, and I'll be matching it. And here, the image is fixed where your template from 16 cross 16, I'll scale down to some 8 cross 8. Then I'll scale down to 4 cross 4. Then I'll scale down to 2 cross 2. Then I'll be going for matching. So here in this case, both the template as well as the image is getting scaled down. So this says that if the face region is very small, how we can go for the further processing. When the face region is too small, what you can do is, this is the face region. The first, here it's mentioned this is only the face region. Instead of having the face region, they have taken face region with some context. Okay, so some surrounding regions. Okay, this is the entire image. Okay, this is the entire image. So it says that with no context, this is Excel where your image size is mentioned as XL, L, M, S, and the extremely small. So for extremely small case, the image with context plays some certain good role. But when in case of Excel, both these two, that is fixed context as well as the proportional context, gives good results. So which means that when the face region is very small, instead of taking the face region, we can extract the surrounding regions so that the features can be somewhat more compared to that of a single one and can be used for detecting. So how this task is done is, your image, it is scaled up by 2 times the original size and scaled down. So for example, here the image, when it is of size 256 cross 256, it is scaled up to 512 cross 512, and here it accepts 256 cross 256, and this accepts 128 cross 128. Okay, so we are passing it to a end-to-end trainable model, and so here are some locations in this. Some images can be detected. Here some images can be detected. Here some images can be detected. All that were fused to get the final decision. This is some example results for face detection. So after detecting the face, we can go for emotion recognition. So I think I can stop here. In the afternoon session, I'll be explaining about these 2 tasks. That is, one is emotion recognition with hands-on, as well as I'll start with the hands-on on background subtraction, and then I'll be explaining about the first one, what is called as emotion recognition, then some activity recognition also we can discuss in the afternoon session.